What if you could step beyond the edge of everything known and experience the universe's ultimate mystery firsthand? Picture yourself drifting in the profound silence of space, drawn toward a darkness so complete it seems to swallow the very stars around it. This is no ordinary void. This is a rotating black hole, a cosmic whirlpool where the laws of physics are stretched, twisted, and rewritten. As the visionary physicist Kip Thorne once described, a black hole warps spacetime so severely that even light cannot escape its grasp. And today, we're going to do more than just talk about that idea. We're going to feel it, live it, and journey through it together. This video is an invitation to explore one of the most extraordinary questions in modern astronomy. What would it truly feel like to fall into a rotating black hole? We'll blend groundbreaking science with immersive storytelling, guiding you through every surreal moment from the first tug of tidal forces to the mind-bending distortions of time and space near the singularity. You'll discover how these spinning giants differ from their stationary cousins, why their inner structure might hide possibilities as strange as wormholes or gateways to other universes, and what your own senses and mind might perceive during this one-way voyage into the unknown. By the end of our journey, you won't just understand the concepts behind rotating black holes, you'll have ventured through them in your imagination, stood at the precipice of reality itself, and felt what it means to cross a boundary beyond which nothing returns. This is more than a scientific exploration. It's a story about curiosity, courage, and the human desire to touch the edges of the cosmos. So let's begin, not as detached observers, but as intrepid travelers, ready to fall into the heart of one of nature's most magnificent and terrifying creations. But to truly grasp the sheer weirdness of what awaits, we first need to understand the engine of this chaos, the rotation itself. Unlike the simpler, stationary black holes you might be familiar with, a rotating black hole is a dynamic, spinning maelstrom governed by a complex set of equations known as the Kerr metric. This spin isn't just a minor detail. It fundamentally reshapes the black hole's entire architecture and the very fabric of spacetime around it. Imagine the difference between a still pond and a powerful whirlpool. A non-rotating black hole is like dropping a rock into that pond. The water dips downward in a symmetrical funnel, but a rotating black hole is that whirlpool where the water doesn't just sink, it's dragged into a furious, spinning dance. That's exactly what happens with spacetime itself. The immense angular momentum of the black hole's mass literally drags the fabric of the universe around with it, a phenomenon physicists call frame dragging. This cosmic dragging creates a remarkable region just outside the event horizon called the Ergosphere. Think of it as a celestial no-parking zone shaped like a flattened sphere that wraps around the black hole's equator. Within the Ergosphere, the drag of spinning spacetime is so overpowering that it becomes impossible to stand still. No matter how powerful your rockets are, you would be forced to move in the same direction as the rotation. You're caught in a current there's no swimming against. This region is where the black hole's rotational energy can, in theory, be tapped, a concept known as the Penrose process, where an object could break apart, with one piece falling in and the other being flung out with even more energy than it came in with. It's like stealing a bit of power from the universe's most powerful turbine. This relentless spin also warps the black hole's most infamous feature, the singularity. In a static black hole, all matter is crushed into a single, infinitely dense point. But here, the rotation flattens that point into a ring singularity. This isn't just a change in shape. It opens up mind-bending theoretical possibilities. Some solutions to the equations suggest this ring might act as a gateway, a portal to other universes or different points in spacetime. though it's crucial to remember this remains firmly in the realm of theory and speculation. What's more tangible is how the spin affects your experience of time. The closer you get to the black hole, the more extreme time dilation becomes, but with rotation, this effect isn't uniform. Time would pass at different rates depending on whether you're moving with the spin or against it, adding another layer of disorientation to the journey. Understanding these properties, the ergosphere, the ring singularity, and the amplified time dilation is essential. They transform a descent into a static void, which is terrifying enough, into a voyage into a dynamically twisted realm that challenges our very understanding of physics and reality. As you drift closer to this cosmic whirlpool, the initial view is both beautiful and terrifying. From a distance, the black hole presents itself as a perfect circle of absolute blackness, a void that seems to swallow all light and hope. Encircling it is a brilliant, chaotic whirl of light, the accretion disk. This isn't just a simple ring, it's a maelstrom of superheated gas and dust, particles torn from nearby stars and accelerated to nearly the speed of light. They crash into each other, releasing a torrent of X-rays and visible light that paints the darkness with fiery hues of blue, white, and gold. It's a mesmerizing, violent ballet of matter on the edge of oblivion. The first physical sensation you'd notice isn't a sound. Space is silent but a pull, an inexorable, gentle tug that steadily grows into an undeniable force. This is the black hole's gravity taking hold, but unlike the uniform pull of a planet, a black hole's gravity has a steep gradient. Your feet, if you're falling feet first, are closer to the black hole than your head. They feel a stronger gravitational pull. This difference in force, however slight at first, begins to stretch your body. This is the onset of spaghettification, a gruesomely apt term for the process of being stretched into a long, thin stream of atoms. In a rotating black hole, there's a slight reprieve. The spin distributes the gravitational forces a bit more evenly, like how the spin of a planet flattens it at the poles. This might delay the inevitable stretching, giving you a few precious extra moments of coherent thought before the extreme tidal forces take over completely. Your view of the universe itself begins to warp around you. This is the effect of gravitational lensing. The black hole's immense mass acts like a giant lens, bending the paths of light from the stars behind it. The familiar constellations smear and distort, stretching into arcs and rings of light that encircle the dark shadow of the black hole. Stars behind the black hole become visible around its edges, their light bent around the void in a perfect, shimmering halo. It's as if you're looking at the entire cosmos through a giant, crystal-clear fishbowl, with reality itself wrapped around this point of infinite density. Simultaneously, you'd experience a profound and disquieting shift in your perception of time. To you, inside your spaceship with your clock ticking normally, seconds feel like seconds. But you know that for anyone watching you from a safe distance, your approach is slowing down, drastically. With every meter you fall, your image from the outside would appear to freeze more and more. Your final moments before crossing the event horizon would be stretched out across an eternity from their perspective. You are falling toward a point where time, as the outside universe knows it, effectively stops. This relativity of experience is one of the most isolating feelings imaginable. You are utterly alone, severed from the universal clock you've known your entire life. The glow from the accretion disk intensifies, bathing everything in a harsh, actinic light. The gentle tug has now become a firm and urgent drag, an insistent river current pulling you toward a waterfall you cannot see. There is no going back. Every instinct screams to fight, to fire thrusters, to escape, but the energy required to break free now exceeds anything possible. You are a leaf caught in a hurricane, and the eye of the storm is this perfect darkness. This approach phase is a unique blend of overwhelming awe at the cosmic spectacle and a deep, primal dread of the inevitable. It's the calm before a storm that defies all physics, a final glimpse of a sane universe before crossing the threshold into the unknown, and then you cross it. There is no bump, no shudder, no dramatic flash of light. The event horizon of a rotating black hole isn't a physical wall you can touch or see. It's a mathematical line in the fabric of the cosmos, a threshold of gravitational dominance from which not even light has the speed to escape. Because of the black hole's intense spin, this boundary isn't a perfect sphere but is instead squashed at the poles and bulging at the equator, an oblate spheroid shaped by the relentless whirl of spacetime itself. Your passage across this ultimate point of no return could be so smooth, so utterly devoid of sensation, that you might not even realize it has happened. There is no cosmic signpost blinking, irreversible doom ahead. One moment you are approaching it, and the next you are simply inside. The laws of physics outside the horizon no longer apply to you. Your fate is now sealed by mathematics. Your visual field, however, undergoes a transformation so bizarre it defies all earthly comparison. If you were to look back the way you came, toward the universe you once knew, you would see it collapsing. The entire cosmos, every star, every galaxy, all of history and future, seems to recede into a single, intensely bright circle of light directly behind you. It's like looking down an infinitely long tunnel toward a pinpoint of light, but that pinpoint contains everything. It's the last light from the outside universe, all focused and lensed into this one brilliant ring, a final snapshot of all that exists frozen in time. It will never change, never dim, never show anything new. It is your last permanent postcard from home. But if you look in the direction of your fall, toward the black hole's core, the view is even more unsettling. Above you, the light from the fiery accretion disk doesn't just surround the blackness. It is warped and bent by the extreme gravity into a dazzling, complex halo. You might see multiple, shimmering phantom images of the disk, layers of light that have orbited the black hole once, twice, or countless times before finally reaching your eyes. It creates a mesmerizing, kaleidoscopic display of luminous rings, a celestial carousel of energy spinning in the profound darkness. This is where the very definitions of time and space begin to unravel. Inside the event horizon, their roles are not just distorted, they are fundamentally swapped. In the normal world, you can move forward, backward, left, and right in space, but you are always forced to move forward in time. Here, that certainty is broken. The singularity ahead of you is no longer just a place in space. It is a moment in your future. Every possible path, every direction you could possibly move, now leads you inexorably toward it. Moving forward in time is no longer a passive experience. It is an active journey toward your own dissolution. You are not just in a place anymore. You are in a process, a river of spacetime that flows in only one direction, toward the end. This silent, imperceptible crossing is perhaps the most profound moment in the entire journey. There was a before, and now there is an after. You have left the universe of your birth and entered a new realm governed by rules we can only guess at with our current physics. You are now a part of the black hole's hidden interior, a place of mystery where gravity reigns supreme and the normal laws of nature cease to have any meaning. The calmness of the crossing belies the incredible violence being done to the very concepts of reality itself. Once you are inside the Ergosphere, you are no longer just falling, you are surfing a wave of spacetime itself. This region is not empty or still. It is a cosmic whirlpool in motion, a place where the very fabric of the universe is being dragged around the black hole at incredible speeds. Imagine trying to swim against a river current so powerful that even Olympic champions would be swept away. Now, replace the water with the fundamental structure of reality, and you begin to grasp the irresistible force at work here. Within the Ergosphere, the black hole's rotation is so dominant that it imposes a universal law. Everything must move in the direction of the spin. Not even light has a choice. Photons, the fastest things in the universe, are caught in this flow, their paths bent into curves and spirals that orbit the black hole. For you, this translates to a sensation of being carried along by an invisible, unstoppable current. No amount of thrust from your ship could allow you to hover or move backward. You are a passenger on this ride with no control over your direction. This bizarre environment isn't just a curiosity, it's a place of incredible energy potential. The dragging of spacetime here is so extreme that it actually stores rotational energy stolen from the black hole itself. This is the basis of the Penrose process, a theoretical method for extracting energy that sounds like science fiction but is grounded in real physics. Here's how it could work. If you were to launch a probe or eject an object into a precise, braking trajectory within the Ergosphere, the immense rotational forces could literally tear it apart. One piece of the object would be captured by the black hole's immense gravity, falling inward and effectively slowing the black hole's spin by a tiny amount. The other piece, however, could be flung back out into space with more energy than it originally had. It's like dropping a ball into a spinning merry-go-round at just the right angle so that it gets kicked back out at a higher speed. In this way, the Ergosphere acts as a cosmic energy bank, allowing in theory for the theft of rotational energy from one of the most powerful objects in existence. While you wouldn't be performing this experiment yourself on your fatal fall, the mere possibility highlights the sheer dynamism of this environment. Your own sense of direction and orientation would become utterly meaningless here. The concepts of forward and backward, which are defined by the geometry of space, are twisted and warped by the spin. The local geometry is so distorted that compasses and gyroscopes would spin uselessly, providing no reliable data. If you tried to point toward what you thought was the black hole's center, your own perception might be fooled by the lensing of light and the frame dragging of space. It would feel less like moving through space and more like space is moving through you, a disorienting and nauseating sensation where your vestibular system, your body's internal gyroscope, would be in constant conflict with the visual madness outside your window. This is a preview of the black hole's true power, a demonstration that it doesn't just crush matter with gravity, it commandeers the very stage upon which physics plays out. The Ergosphere is a violent and dynamic arena, a testament to the fact that a rotating black hole is not a passive pit but an active, energetic engine that reshapes its surroundings. This intense distortion of reality is just a taste of the even more extreme effects that await as you are pulled further inward, closer to the heart of the darkness. Inside the event horizon, your own watch would continue its steady tick, a familiar rhythm in a world that has become profoundly unfamiliar. Your heart would beat at its normal pace, your thoughts would unfold at their usual speed. To you, time feels utterly normal. This is the deeply personal and isolating reality of relativity, but that normalcy is a complete illusion when viewed from the outside. To any observer safely watching from a distant star, your final approach to the event horizon would be a spectacle of infinite slowness. As you neared that invisible boundary, your image would begin to fade and redden, your movements would stretch into imperceptibility, and your final moment of crossing would be frozen in their view for all of eternity. You would appear to hang there forever on the brink, a permanent monument to the moment you were lost. This isn't a trick of the light, it's a fundamental property of gravity warping time itself. The closer you get to a massive object, the slower time runs relative to areas of weaker gravity. At the event horizon, this effect becomes infinite time for you, effectively stops from the outside perspective. You have become a living photograph, a memory etched onto the edge of nothingness. The rotation of the black hole takes this already strange phenomenon and twists it into something even more complex. The frame dragging caused by the spin means that spacetime itself is being whipped around the black hole like a cosmic vortex. This motion creates a gradient in time dilation. If you were to move in the direction of the spin, time would pass for you at a slightly different rate than if you tried to move against it. It's as if you're running on a moving walkway at an airport. Going with the direction of the walkway makes your relative speed different than going against it. In the ergosphere, this effect is so pronounced that it could mean two clocks placed just meters apart, one circling with the spin and one resisting it, would quickly fall out of sync. Your own left side might be experiencing time at a subtly different rate than your right side, depending on your orientation to the rotation. This isn't just a mathematical curiosity. It's a physical sensation that would add a layer of nauseating disorientation to your fall, as the very flow of causality becomes warped and uneven around you. One of the most profound and speculative consequences of this extreme time dilation is the possibility of witnessing the future. As you fall and your personal time continues its steady march, the light from the entire external universe is being accelerated from your point of view. Billions of years of cosmic history could, in theory, flash before your eyes in a matter of seconds. You might see stars dying, new galaxies forming, and the eventual heat death of the universe itself, all playing out in a silent, hyper-accelerated movie projected onto the collapsing circle of light behind you. It's a thought that borders on the philosophical, the ultimate, tragic irony of being present at the end of all things moments before your own end. However, it's crucial to emphasize that this is a prediction based on extending the equations of general relativity to their limit. Most physicists believe the intense radiation and tidal forces would make actually observing this impossible, or that quantum effects would change the rules entirely. But as a thought experiment, it highlights the sheer scale of the temporal distortion at work, where a single second for you could encapsulate an eon for the cosmos. This splitting of reality into two different timelines, your own steady experience and the frozen, infinite view from the outside, strikes at the very heart of causality and our understanding of a universal now. There is no single objective clock for the universe. Your now and the distant observer's now are not the same moment, and near a black hole, that difference is stretched into a chasm. This challenges the most intuitive aspects of how we perceive the world, suggesting that time is not a river flowing at the same speed for everyone, but a vast, malleable ocean where currents flow at different rates. The temporal chaos you experience is more than just a side effect. It is a fundamental demonstration that the universe operates by rules that are deeply foreign to our everyday lives, revealing a reality that is far stranger and more wonderful than we could ever perceive from the safety of our own planet. This relentless inward journey brings you toward the heart of the mystery, the final destination for all that falls into a black hole, the singularity. But if you're expecting a single, infinitely dense point of crushing doom, the rotating black hole has a surprise in store. Thanks to its incredible spin, the singularity here is not a point. It is a ring. Imagine the difference between a needle and a bracelet, or a dot and the letter O. This ring singularity, a direct consequence of the Kerr solution to Einstein's equations, completely changes the rules of the game and the nature of your potential fate. This ring isn't just hovering in space, it's rotating at a significant fraction of the speed of light, and its geometry is bizarre beyond belief. the mathematics suggest that the very center of this ring might not be a place of infinite gravity. In fact, some solutions to the equations indicate that the gravitational forces could even drop to zero at the exact center, a concept that turns everything we think we know about singularities on its head. This opens up a theoretical possibility that is the stuff of science fiction. If you could somehow navigate your trajectory with perfect precision to pass directly through the center of this ring, you might not be annihilated by infinite tidal forces. Instead, you could, in theory, pass through it, and what lies on the other side? The equations are tantalizingly vague but incredibly suggestive. One possibility is that you would emerge into a completely different region of spacetime, another universe with its own physical constants, or perhaps a different time in our own universe. Another concept is that you might enter a hypothetical region of spacetime called a Einstein-Rosen bridge, a wormhole that could act as a shortcut to a faraway part of our cosmos. It's a breathtaking idea that a black hole, the ultimate symbol of finality and destruction, could actually be a gateway, a cosmic toll booth on an infinite highway of universes. However, and this is a monumental however, this remains entirely in the realm of mathematical speculation. There is no experimental evidence for other universes or stable, traversable wormholes. Most physicists believe that quantum effects, which are not included in the classical theory of general relativity, would likely make such a passage impossible. The ring might be unstable, or the energies involved so extreme that any complex structure, like a human being or a spaceship, would be torn apart by chaotic, unpredictable forces long before reaching the central void. The dream of a gateway is seductive, but it is balanced on a razor's edge of unproven theory. Your experience approaching this ring would be utterly alien. Instead of being stretched in one direction and compressed in another, the tidal forces around a ring singularity are far more complex. The forces would pull and push at you from different directions in a violent, chaotic dance. It might feel less like being stretched into spaghetti and more like being caught in a cosmic blender, with forces twisting and contorting your body in unpredictable ways. This complexity might, for a brief moment, create pockets where the tidal forces are not immediately lethal, offering a fleeting instant of coherent experience before the final dissolution. But this is a small mercy, as the end result is almost certainly the same. Your body and your ship would be reduced to your most fundamental particles, your mass and energy adding to that of the black hole. The nature of this ring singularity is the ultimate question mark at the center of our journey, a symbol of the limits of our knowledge and the thrilling, terrifying possibilities that lie at the edge of physics. Now, as you're pulled deeper into the gravitational whirlpool, the most visceral and physically terrifying aspect of the descent begins, the inexorable pull of tidal forces, a process famously known as spaghettification. The name itself paints a vivid, if unsettling, picture. In a non-rotating black hole, this would be a brutally quick and efficient affair. The difference in gravity between your head and your feet is so astronomically vast that you would be stretched into a long, thin stream of atoms almost instantaneously, like a piece of spaghetti. But here, within the spinning chaos of a Kerr black hole, the experience is markedly different and strangely, slightly less immediately catastrophic. The rotation of the black hole fundamentally changes the geometry of the gravitational field around it. Imagine the difference between stepping into a deep, still well and being caught in a powerful, spinning vortex. In the well, you fall straight down and the pull is direct and uniform from all sides. In the vortex, the motion of the water creates a more complex set of forces. Similarly, the spin of the black hole flattens it at the poles and causes it to bulge at the equator, which in turn makes the gravitational gradient. the rate at which the pull increases less severe in the regions near that equatorial plane. If your trajectory carries you through this zone, the dreaded stretching doesn't happen all at once. It becomes a more gradual and perhaps more horrifyingly perceptible process. You wouldn't feel a sudden snap, but rather a slow, creeping tension. It would begin as a faint pull at your ankles, a sensation that someone is gently but firmly tugging you downward. This pull would steadily intensify, traveling up your calves, your thighs, through your torso. Your body, a structure built for Earth's gentle gravity, is now responding to forces it was never designed to withstand. Your spine would begin to elongate, and you'd feel a profound and unsettling pressure in your joints. Simultaneously, the forces would act from the sides, compressing your ribs and shoulders inward. It's a dual sensation of being pulled apart and squeezed together at the same time, a feeling of being sculpted into a new, impossible shape. This isn't just happening on a macroscopic level, it's a molecular nightmare. The atoms that make up your body all experience this tidal force differently. The atoms in your toes are pulled just a fraction more strongly than the atoms in your heels. The bonds between molecules are strained beyond their limits. In these final moments, you are not so much a human being as you are a collection of particles being sorted by gravity. The very concept of you is being physically deconstructed. Yet, because of the rotation, this entire gruesome unraveling might unfold over several seconds, or even longer, rather than in a split-second blur. This grants a dreadful window of consciousness, a few precious heartbeats where you are acutely, tragically aware of the transformation occurring to your own body. It's a paradoxical gift of time within a place where time itself is breaking down, allowing you a final, horrific awareness of your own dissolution against the most extreme backdrop in the universe. While the physical forces are reshaping your body, your visual field is undergoing a transformation so profound it would challenge your very sanity. The black hole's gravity doesn't just pull on matter, it bends the very path of light itself, creating a celestial funhouse mirror on a cosmic scale. This is the phenomenon of gravitational lensing, and near a rotating black hole, it becomes the dominant feature of reality. The first thing you would notice is the complete reorganization of the cosmos around you. Every single star, every distant galaxy, is no longer in its rightful place. Instead of a blanket of pinpoint lights against a black void, the entire universe seems to have been smeared across the dome of the sky, stretched and warped into a brilliant, shimmering halo that completely encircles the black hole's shadow. It's as if you are sitting at the bottom of a well, looking up at a distorted view of the entire night sky, wrapped into a single, blindingly bright ring of light directly above you. This is the last light from the outside universe, all focused and lensed by the black hole's gravity into this one final, breathtaking panorama. The accretion disk, that maelstrom of superheated matter you saw on your approach, undergoes an even more bizarre metamorphosis. From your perspective inside the Ergosphere, it no longer appears as a flat ring circling the equator. Instead, the light from the top and bottom of the disk is bent over and under the black hole's shadow, wrapping it completely. You wouldn't see a simple band, you would see a complex structure of luminous rings. There might be a primary, intensely bright ring that seems to form a waist around the darkness, but above and below that, you would see fainter, duplicate images, ghosts of the disk where light has been bent on ever more extreme paths. Some of this light has orbited the black hole once before escaping to your eyes. Some has circled twice or even dozens of times, creating a nested series of rings, each one fainter and more redshifted than the last, like a target painted in fire and light with the perfect blackness at its center. This leads to the most mind-bending optical illusion of all, the possibility of seeing phantom images of yourself. Imagine light photons reflecting off your spacecraft or your suit a fraction of a second after you crossed the event horizon. Some of those photons would travel on paths that send them on a full, or even partial, orbit around the black hole before looping back to hit your eyes. The result, you might catch a glimpse of your own back from moments ago, seemingly hanging in space in front of you. You could see multiple fading images of your own descent, a ghostly parade of your past selves, each one representing a previous orbit of light. It's a visceral, personal demonstration of the warped geometry you're trapped within, making the disorientation not just an abstract concept but a direct and unsettling personal experience. The combination of these effects, the universe compressed into a single ring, the accretion disk wrapped into a complex lattice of light, and the phantom images of your own journey, creates a visual field that is utterly impossible to pass with any earthly intuition. Your brain, evolved to understand light traveling in straight lines, is completely fooled. There is no way to judge distance, scale, or even the true number of objects you are seeing. This carnival mirror reality is both terrifyingly chaotic and achingly beautiful, a final, magnificent light show painted by the most extreme physics in the universe. It is the ultimate testament to the fact that you have left a world of normal geometry and entered a realm where space itself is tied into knots. Yet amidst this crushing silence, your brain, a master pattern recognizer forged in a world rich with sensory input, would rebel against the void. It would desperately try to make sense of the incomprehensible, translating raw, violent energy into the only language it knows, sensation. While no sound waves can travel through the vacuum, your spacecraft itself would become an instrument of phantom noise. Intense vibrations from the swirling maelstrom outside, the shuddering impact of high-energy particles from the accretion disk striking the hull, the subtle groaning of the ship's structure as tidal forces begin to stress it, would travel through the frame and into your body. Your inner ear, attuned to detecting vibrations, might interpret these relentless, rhythmic tremors as a deep, pervasive hum, a sinister drone that seems to emanate from the very fabric of space around you. It wouldn't be sound as we know it, but a physical vibration perceived as noise, a bone-deadening soundtrack to your descent. Beyond this, the environment itself is so charged with energy that it could directly stimulate your senses in bizarre ways. The furious torrent of radiation, X-rays and gamma rays pouring from the superheated plasma of the accretion disk would be bathing you. At these intensities, that radiation could potentially trigger faint, phantom signals in your optic nerves, causing you to see faint flashes of light that aren't there, like a continuous, silent fireworks display behind your eyes. Similarly, the barrage of high-energy particles might interact with your nervous system directly, creating false sensations akin to the pins and needles of a limb falling asleep, but spreading across your entire body. These wouldn't be hallucinations in the psychological sense, but rather physiological illusions, your body's hardware being hacked by the extreme physics of your environment. Perhaps the most profound sensory failure would be the loss of proprioception, your brain's innate sense of where your body is in space. This is the sense that lets you close your eyes and still touch your nose with your finger. As the tidal forces of the black hole begin their work, stretching your body, this internal map would become horrifically distorted. The signals from the nerves in your legs, which are being pulled away from you, would become delayed and confused. Your arms, being compressed inward, would send conflicting data. Your brain would receive a jumbled, impossible mess of positional information that simply cannot be reconciled with a lifetime of experience. The result would be a terrifying feeling of disembodiment, a dissociation where you feel untethered from your own physical self. You might feel as though you are floating outside your body, watching it deform, or lose all sense of its boundaries altogether, merging with the cold, vibrating metal of your ship. This complete breakdown of your most fundamental sense of self, combined with the phantom hum and the silent flashes of light, creates a sensory panorama of utter isolation and otherworldliness. It is a symphony of illusion played on the instrument of your own nervous system, a final, cruel trick of physics that makes the reality of your situation feel even more unreal, underscoring that you have traveled beyond anywhere any human was ever meant to be. The initial flood of terror is an almost primal response, a hardwired reaction to the ultimate existential threat. Your rational mind, armed with the grim certainty of physics, knows there is no force in the universe that can reverse your course. This isn't like being lost at sea with a fading hope of rescue. This is the absolute mathematical certainty of oblivion. That realization would trigger a cascade of panic, a heart-pounding, breath-stealing wave of pure dread. Every instinct screams for a fight or flight response, but there is nothing to fight and nowhere to flee. You are utterly and completely trapped. This raw, animalistic fear would likely dominate those first moments after the irreversible crossing, a suffocating cloak of panic in the profound silence. But the human mind is remarkably adaptable even in the face of the impossible. As the seconds tick by on your own personal clock, a new emotion would begin to well up, slowly eclipsing the terror, an overwhelming, soul-stirring awe. The visual spectacle surrounding you is unlike anything any human has ever witnessed. The entire cosmos is wrapped around you in a brilliant halo of light, a tapestry of distorted stars and nebulae. The accretion disk churns in a mesmerizing dance of energy, a complex lattice of fire and shadow. You are at the very center of the most extreme physical phenomenon in existence, a front-row seat to the universe's most magnificent and violent ballet. The sheer, incomprehensible scale and power of it all couldn't help but evoke a profound sense of your own insignificance. You are a fleeting whisper against a cosmic roar, a single, momentary thought in the infinite mind of the universe. This feeling isn't demeaning, it's strangely humbling and liberating. The weight of your own mortality, your earthly worries and desires, begins to feel trivial, washed away by the grandeur of the spectacle. This shift from terror to awe might be aided by your own biology. In situations of extreme, inescapable stress, the brain has its own survival mechanisms. It's theorized that it might release a cocktail of neurotransmitters like endorphins or dopamine, not to save the body but to soothe the mind. It's a final act of mercy from your own neurology, inducing a state of euphoria or transcendent calm. This isn't just speculation. We see echoes of it in near-death experiences reported by individuals on Earth, who often describe feelings of peace and connection in their final moments. Here, faced with the ultimate conclusion, your mind might grant you a state of heightened awareness, a hyper-clarity where you absorb every detail of the unfolding cosmic drama. The panic recedes, replaced by an intense, almost childlike curiosity. What will happen next? What does the singularity truly look like? You become an active observer of your own dissolution. This journey through fear into awe and finally toward acceptance is the profound psychological arc of the fall. Acceptance doesn't mean a happy ending, it means a cessation of struggle. It is the quiet, solemn understanding that you are witnessing the final, beautiful truth of the universe, that all things, even stars and consciousness itself, are transient patterns in the flow of spacetime. Your individual story is ending, but you are becoming a permanent part of a far grander story, your mass and energy merging with the black hole to become part of its future evolution. This emotional roller coaster, from the most base human fear to a state of near philosophical transcendence, is arguably as significant as the physical distortions of spacetime. It is the human response to the infinite, a final, internal voyage that mirrors the external one, proving that even on the edge of oblivion, the capacity for wonder remains our most defining trait. As the tidal forces begin their inexorable work on your body, an even more profound transformation is occurring within your own mind. The extreme time dilation near the event horizon doesn't just affect clocks, it warps the very fabric of your consciousness. While an outside observer would see your final moments stretched across an infinite span of time, your own internal experience would be rushing forward at an unimaginable rate. Your neural processing, the electrical dance of thoughts and memories, could accelerate to a breathtaking speed. It's as if your brain, operating within its own local time frame, gets put on fast forward while the entire universe outside grinds to a halt. This cognitive acceleration could unlock a flood of memories with a clarity and intensity beyond anything experienced in normal life. Your entire personal history might unspool before you in a matter of heartbeats. You wouldn't just remember your first day of school, you would relive the warmth of the sun on your face, the rough texture of the backpack strap on your shoulder, the specific scent of chalk dust and waxed floors. A lifetime of conversations, emotions, and sensations could crash over you in a hyper-detailed, immersive cascade. This isn't a simple slideshow of your life, it's a total re-experiencing, a final, comprehensive integration of everything that made you who you are. Some theories in neuroscience suggest that in extreme stress, the brain can release a flood of neurotransmitters that dramatically enhance recall and perception, as a final attempt to find a solution to an unsolvable problem. Here, with no solution possible, that mechanism might instead grant you a panoramic view of your own existence. Simultaneously, your perception of the external cosmos would become a wildly accelerated spectacle. The light from the outside universe, funneled into that brilliant, shrinking circle above you, would carry the entire future history of everything. Billions of years of cosmic evolution could flash before your eyes in a blinding, silent montage. You might witness the slow dance of galaxies as they collide and merge, the fiery death of our sun, the cold fade of all stars in the distant future, all compressed into a few seconds of subjective time. Your consciousness becomes a time telescope, seeing the ultimate fate of the very universe that created you. This creates a surreal and paradoxical state of being where your internal world, your past, and the external world, the cosmos's future, are both rushing toward you at once, collapsing the distinction between memory and prophecy, between what was and what will be. The rotation of the black hole adds another bizarre layer to this temporal chaos. The frame-dragging effect means that the flow of time isn't uniform around you. If you were to turn your head toward the direction of the spin, time might seem to flow at a different rate than if you looked in the opposite direction. This isn't just a mathematical abstraction. It could create a genuine, perceptible disorientation within your own stream of thought. Your sense of a unified now would shatter. It might feel as though different parts of your brain are processing information at slightly different speeds, leading to a dreamlike, dissociative state where linear causality itself begins to break down. Thoughts would not simply lead to other thoughts in an orderly chain. They might branch, loop, and overlap in a non-linear jumble, blurring the line between reality, memory, and pure imagination. This is the ultimate distortion, where the gravity of the black hole doesn't just bend light. It bends the very progression of consciousness, offering a fleeting, terrifying glimpse into a mode of existence where time is not a river but a vast, interconnected ocean. And so we arrive at one of the most captivating and speculative ideas in all of theoretical physics, the notion that this journey might not be an end but a beginning. As you are pulled toward that enigmatic ring singularity, a final, desperate question arises. Could this be a gateway? The equations of general relativity, in their pure classical form, do indeed offer a tantalizing possibility. An Einstein-Rosen bridge, more popularly known as a wormhole, is a valid solution to these equations. In this breathtakingly elegant idea, the black hole you fell into could be connected to a white hole, a theoretical region of spacetime where matter and energy are violently expelled rather than absorbed. This would form a cosmic tunnel, a shortcut through the fabric of the universe that could, in theory, connect two distant points in space or even two entirely different universes. The Ring Singularity at the heart of a rotating Kerr black hole is the key that makes this idea even more plausible than in a static black hole. A point singularity is an undeniable dead end, a wall of infinite density. But a ring, its hollow center presents a geometric loophole. The mathematics suggest that if you could somehow navigate a trajectory that takes you directly through the center of this spinning ring, you might avoid the region of infinite curvature altogether. You would not be annihilated, but would instead emerge from the other side, perhaps into a different region of spacetime. It's a concept that feels ripped from the pages of the most ambitious science fiction, the ultimate cosmic cheat code, turning the universe's most efficient destroyer into its most incredible transportation system. However, this is where we must temper wonder with a heavy dose of scientific reality. These wormhole solutions, while mathematically beautiful, are almost certainly physically impossible. They are predicated on a perfect, clean, vacuum solution to Einstein's equations, a reality that ignores the messy, complicated laws of quantum mechanics. Most physicists believe that the moment you introduce any real matter or energy into this system, like, for instance, a human being trying to pass through, the delicate structure would collapse. The incredible energies and violent fluctuations at the quantum level would likely snap the throat of the wormhole shut instantaneously, or create an impenetrable barrier of energy known as a quantum firewall that would vaporize anything attempting the passage. Furthermore, even if the tunnel remained open, the forces inside would be unimaginably chaotic. The tidal forces would not be the smooth, predictable pull of gravity, but a violent, twisting chaos that would shred any complex structure into its subatomic components long before any hoped for emergence. So, while the idea of a gateway offers a narrative thread of hope, a potential escape from the bleak fate of spaghettification, it remains a fascinating thought experiment rather than a viable prediction. It represents the outer limits of where our current understanding of gravity breaks down and where a new theory of quantum gravity must take over. This possibility, however remote, adds a profound layer of mystery to the final moments of the fall. It transforms the singularity from a simple crusher of matter into a symbol of the unknown, a question mark at the heart of physics. Your journey toward it becomes not just a voyage to your end, but a voyage to the very frontier of human knowledge, a place where our deepest questions about the nature of reality remain, for now, unanswered. The final approach to the Ring Singularity is where the abstract horror of physics becomes a devastatingly personal reality. The chaotic dance of tidal forces you've experienced so far now escalates into an all-out assault. That gradual stretching sensation vanishes, replaced by an overwhelming, violent pull that operates on a subatomic level. You are no longer being gently sculpted by gravity. You are being unraveled by it. The difference in gravitational pull between your head and your feet, which was once a curious sensation, now becomes an immeasurable chasm. Every single molecule in your body is simultaneously pulled downward with a force that makes the bonds holding it together seem insignificant. You are not just a person being stretched, you are a structure undergoing a catastrophic and instantaneous deconstruction. In a rotating black hole, this process is uniquely chaotic. The spin that once offered a slight reprieve now introduces a terrifying unpredictability. the forces aren't uniform like a steady pull from a single direction. Instead, the complex whirling geometry of the Ring Singularity creates a maelstrom of gravitational gradients. You wouldn't feel a smooth, linear stretch. It would be a violent twisting and shearing motion, as if different parts of your body are being pulled in subtly different directions simultaneously. One arm might be wrenched forward while the other is lagging behind. Your torso could experience a crushing torsion that your brain simply has no reference point to understand. This isn't an orderly dissolution into a stream of particles. It's a chaotic shredding, a fundamental breakdown of your physical form into its most basic components. The concept of pain, as we understand it, likely becomes irrelevant almost instantly. The nerve endings that would register such agony are themselves being torn apart, their signals lost in the storm before they can even reach a brain that is itself coming undone. Your consciousness wouldn't have time to process a sensation of pain in the conventional sense. Instead, the experience would be one of profound and total physical disintegration. Your atoms, those building blocks that have been you since birth, are now being pried apart. The electrons are stripped from their orbits. The nuclei themselves are stressed to the point of fragmentation. In a matter of moments, the intricate, beautiful structure that was a human being is reduced to a chaotic stream of elementary particles, a cloud of quarks, leptons, and photons, all hurtling toward the same destination. This is the absolute end of individuality. The information that defined you, your memories, your thoughts, the unique pattern of your neural connections, is scrambled beyond any conceivable recovery. Your mass, your energy, is absorbed into the black hole, adding to its total and causing its event horizon to shimmer and expand by an infinitesimal amount. You become a permanent part of the black hole's structure, your particles merging with the fundamental fabric of spacetime that constitutes the singularity itself. It is a transition from being a distinct entity to becoming an anonymous contributor to the mass of one of the universe's most enigmatic objects. This is the bleak, inescapable finale predicted by our current understanding of general relativity. A total and complete return to the universe's most basic ingredients, a dissolution into nothingness. Yet even as your physical form is torn apart and absorbed into the black hole's mass, a profound question remains echoing in the theoretical void. Does anything of you actually persist? According to the bedrock principles of quantum mechanics, information, the specific, unique arrangement of particles that defined you, can never be truly destroyed. It might be scrambled, transformed, or rendered utterly unrecognizable, but the quantum information that encoded your memories, your thoughts, and the very structure of your atoms is fundamentally indestructible. This creates one of the greatest paradoxes in modern physics when it collides with the classical picture of a black hole. If nothing, not even light, can escape from behind the event horizon, then how can that information ever get out? It seems to be trapped forever, violating a core tenet of quantum theory and presenting a glaring contradiction that physicists call the black hole information paradox. This is where the revolutionary work of Stephen Hawking enters the story. He discovered that black holes are not completely black. Due to weird quantum fluctuations occurring right at the very edge of the event horizon, black holes slowly emit a faint glow of particles, now known as Hawking radiation. This process causes the black hole to gradually lose mass and, over unimaginable eons, evaporate completely out of existence. But here's the catch. Hawking's initial calculations suggested this radiation was completely random, carrying no information about what fell into the black hole. It would be like burning a library full of unique books and having only featureless, identical ash remain. The information seemed to be lost forever, which quantum mechanics says is impossible. This set off a decades-long debate that is still not fully resolved, a fundamental conflict between the two pillars of modern physics, general relativity and quantum mechanics. For you, the hypothetical faller, this sparks a truly bizarre possibility. As the black hole containing your particles very slowly radiates itself away over trillions of years, some theorists believe that the information that once was you is not lost. Instead, it could be imprinted onto this Hawking radiation in some incredibly complex, scrambled code. Your essence, not your consciousness or your soul, but the quantum-level blueprint of the particles that made you might be slowly leaked back out into the universe, one particle at a time. It would be the ultimate dissociation, your existence smeared across the lifespan of the cosmos. Of course, this is a cold comfort. This you would be irretrievably mixed with the information of every other star, rock, and particle that ever fell in, a chaotic puzzle that could never be reassembled. You would become a permanent part of the universe's background static, a whisper lost in the cosmic noise. The complex geometry of a rotating black hole adds fascinating layers to this quantum puzzle. The intense frame dragging and the presence of the ergosphere could significantly alter the nature of those quantum fluctuations at the horizon. The radiation emitted might have a different character, a different energy signature, or a different way of encoding information compared to a static black hole. Some physicists speculate that the spin might even make information recovery slightly less improbable, though it remains an astronomically complex task. This theoretical debate is far from just an academic exercise. It forces us to confront the very nature of reality and pushes us toward a deeper theory of quantum gravity that can reconcile how information behaves in the most extreme environments the universe can concoct. Your hypothetical fall, therefore, doesn't just end at the singularity. It becomes a permanent part of a deep and ongoing cosmic mystery. But to truly appreciate the bizarre complexity of a rotating black hole, we need to contrast it with its simpler, far more brutal cousin, the non-rotating Schwarzschild black hole. Imagine the difference between being caught in a complex, swirling tornado and simply stepping off the edge of an infinitely tall cliff. The Schwarzschild black hole is that cliff, a perfectly symmetrical, static pit of gravity. There is no spin, no whirling drama, just a pure, undistilled, and immediate point of no return. Without rotation to flatten it, the event horizon is a perfect sphere, and the gravitational pull is direct and unforgiving from every direction. This simplicity makes the experience of falling in far more violently efficient. The process of spaghettification isn't a gradual, discernible stretching. It's a sudden and catastrophic snap. The difference in gravity between your head and your feet becomes overwhelmingly lethal almost instantly. There is no ergosphere, no region of frame dragging to slightly mitigate the forces or offer a bizarre window of consciousness. You wouldn't have those extra seconds to perceive the optical illusions or process the disorientation. The tidal forces would act with a swift and terrible finality, pulling you into a single, thin stream of atoms in a fraction of a second. It is a much more direct and in some ways more merciful end, a quick and brutal demolition by gravity, and at the heart of it all lies the ultimate dead end, a point singularity. Unlike the ring-shaped gateway theorized in a Kerr black hole, the Schwarzschild singularity is a single, infinitely dense point of zero volume. There is no hollow center to aim for, no geometric loophole, no theoretical possibility of a wormhole or passage. Every path leads directly and unambiguously to this single point of infinite curvature, where the laws of physics break down completely. Your journey ends not with a question mark, but with a definitive, crushing period. The experience, while terrifying, is conceptually simpler. It is a story of pure destruction, a one-way trip to a definitive and uncomplicated end. the introduction of rotation fundamentally changes this narrative. Spin adds layers of complexity that transform the fall from a simple tragedy into a surreal odyssey. The formation of the Ergosphere creates a dynamic zone of interaction before you even reach the event horizon. Frame dragging warps the flow of spacetime itself, making your path more complex and slightly delaying the moment of spaghettification, granting you those precious, horrifying extra moments of awareness. And the transformation of the singularity from a point into a ring opens up a universe of theoretical possibilities, however remote, that simply do not exist in the static model. The rotating black hole is less immediately hostile in a physical sense, but far more hostile to your understanding of reality. It trades brute force destruction for a more complex, mind-bending unraveling of physics and perception. This comparison isn't just academic, it highlights the incredible diversity of these cosmic objects. Just as no two storms on Earth are identical, no two black holes offer the same experience. Their mass, their charge, and most importantly their spin, dictate a unique and terrifying fate for anything that ventures too close. Up until now, we've painted a picture of a relatively clean, almost serene descent into the darkness, focused on the pure distortions of gravity. But the reality for most black holes is far more violent and spectacular. Many of these cosmic giants are not isolated voids. They are active, feeding beasts, and that feast creates a maelstrom of energy that would utterly dominate your experience long before the more abstract effects of spacetime curvature even had a chance to begin. This is the realm of the accretion disk, a cosmic killing field of incandescent plasma that adds a brutal, practical layer of danger to our hypothetical journey. Imagine approaching what you thought was a dark pit in space, only to be blinded by a light brighter than 1,000 suns. The accretion disk is a vast, swirling whirlpool of superheated gas, dust, and shredded stars, all caught in the black hole's gravitational grip. As this material spirals inward at nearly the speed of light, particles collide with unimaginable violence, converting their immense kinetic energy into a torrent of radiation across the entire electromagnetic spectrum. You wouldn't just be flying toward a dark shadow, you'd be diving headfirst into the heart of a cosmic fusion reactor, one that makes the core of our sun seem placid by comparison. The sheer intensity of this light and heat would be the first truly tangible threat you'd encounter, a palpable wall of energy that would begin to cook you and your ship from millions of kilometers away. This isn't just a matter of uncomfortable warmth, it's instant, total incineration. Long before tidal forces could even begin their gruesome work of spaghettification, the X-rays and gamma rays pouring from the disk would deliver a lethal dose of radiation. Your body would be bombarded by photons so energetic they would shred your DNA and disrupt the fundamental chemistry of your cells. The exterior of your spacecraft, no matter how advanced, would begin to ablate and vaporize, its metals melting under the relentless onslaught. In many realistic scenarios, you would be reduced to a cloud of disassociated atoms long before you ever crossed the event horizon, your journey ending not with a strange physics paradox, but with a simple, violent flash of energy. This harsh reality check reminds us that while the physics beyond the horizon is fascinating, the practical barriers to even getting there are almost insurmountably hostile. The disk's violence isn't random chaos, it's a structured fury that is deeply connected to the black hole's spin. Because the disk's material follows the warped spacetime around the black hole, its rotation naturally aligns with the spin axis of the black hole itself. This co-rotation creates a stable, incredibly powerful dynamo effect. Immense magnetic fields are generated and twisted by this rapid motion, channeling some of the infalling material not inward but outward. These are the spectacular relativistic jets, narrow beams of plasma that shoot out from the poles of the black hole at nearly the speed of light, stretching for thousands of light years into intergalactic space. If your trajectory happened to take you anywhere near the path of one of these jets, the experience would be brief beyond comprehension. You would be vaporized by a focused beam of energy that outshines entire galaxies, a literal cosmic particle accelerator turned against you. Even if you avoided the jets, the magnetic fields within the disk itself would pose a unique and bizarre threat. These fields are so powerful they can accelerate particles to extreme energies, creating a haze of deadly cosmic rays that permeates the entire region. Your ship's electronics would be fried by electromagnetic pulses, and your own nervous system could be disrupted by the barrage. The combined effect of the blinding light, the crushing heat, the lethal radiation, and the turbulent magnetic chaos creates an environment so extreme that it pushes the limits of what we can even physically describe. It transforms the black hole from a passive gravitational well into an active, energetic engine, a place where the raw power of gravity is converted into the most violent forms of energy in the universe. This isn't just a theoretical danger, it's a vivid reminder that real black holes are the most efficient and destructive converters of matter into energy that we know of, and any close approach is a journey into a furnace that makes the fall itself almost a secondary concern. But your experience of this entire surreal descent, from the first tug of gravity to the final moments at the singularity, would be dramatically different depending on one crucial factor: the angle of your approach. The spin of a Kerr black hole creates a cosmic geography, an environment with distinct poles and an equator, and your path through this warped landscape dictates everything you would see and feel. Imagine the difference between rafting directly through the swirling center of a massive whirlpool versus skimming along its outer edge. One route throws you into the heart of the chaos, while the other offers a slightly more orderly, though no less fatal, journey. Choosing to fall in along the black hole's equatorial plane is like signing up for the full, dizzying spectacle of its rotation. This is where the frame-dragging effect is at its absolute maximum. Spacetime itself is being dragged around the black hole here like a powerful, invisible current, and you would be caught in its flow immediately. Your descent wouldn't be a straight plunge inward, it would become a spiraling, orbital dance. You'd be swept along, compelled to move in the same direction as the black hole's spin, adding a powerful sideways velocity to your fatal inward pull. This motion would make the phenomenon of the Ergosphere intensely personal. You would physically feel the impossibility of holding a stationary position, as if some immense, unseen hand were constantly pushing you along a predetermined circular path. The optical illusions would be at their most extreme here too. From this vantage point, you'd have a front-row seat to the full, kaleidoscopic wraparound of the accretion disk and the phantom images of your own past self, creating a visual carnival of light and shadow that spins around you. This equatorial path also dictates the nature of the tidal forces that will eventually pull you apart. Because you're moving parallel to the equator, the differences in gravity act in complex ways. You'd experience the classic spaghettification, stretching lengthwise and compression sideways, but the rotation adds a shearing, twisting quality to the force. It wouldn't be a clean pull, it would feel more like being drawn and quartered by an invisible machine, with the forces working on you from multiple angles as you spiral inward. This is the path of maximum sensory input, a route that assaults you with every bizarre effect the rotating black hole has to offer before you meet your end. In stark contrast, a polar approach, falling in directly over the black hole's north or south pole, offers a completely different, and in some ways even stranger, experience. Here, you are diving into the whirlpool along its axis of rotation, avoiding the most violent sideways currents of frame dragging. the effect isn't absent, but it's significantly minimized. Your fall would feel more direct, a more straightforward plunge toward the central singularity without the powerful spiraling motion. You might even feel a fleeting, false sense of control, as your path seems more predictable and linear. But straightforward is a relative term near a black hole. While you'd avoid the extreme orbital drag, the overall gravitational distortion is just as powerful. Your view would be utterly unique. Instead of seeing the accretion disk as a ring around the equator, you would be staring directly down at it from above. It would appear as a vast, luminous plain stretching out beneath you, a sea of fire that you are falling toward. The light-bending effects would be no less dramatic, but they would manifest differently. The entire disk might appear to warp upward around the edges of the black hole's shadow, creating a breathtaking, bowl-like structure of light that seems to rise up and envelop you. The phantom images and multiple rings of light would be symmetrically arranged around your line of fall, a perfect, hypnotic target of concentric circles. The tidal forces on a polar trajectory would also present a different character. Without the strong rotational shear, the stretching might feel more pure and direct, a clean, overwhelming pull along the axis of your body. However, the structure of the ring singularity itself means that your final approach could be even more chaotic. Falling toward the pole of a ring is a geometrically complex problem, and the gravitational gradients could become wildly unpredictable in the last moments, potentially leading to a more violent and tumultuous dissolution than on the equatorial plane. There is no safe path, only different flavors of cosmic doom. This variability underscores a profound truth about these cosmic monsters. There is no single, universal experience of falling into a black hole. Your personal journey into the unknown is as unique as the path you take, a final testament to the complex and dynamic nature of these incredible engines of gravity. The journey we've been imagining, this mind-bending plunge into a spinning cosmic abyss, feels like the stuff of the most far-fetched science fiction. And for most of human history, that's exactly what it was. The very idea that such an incredible object could exist in reality began not with a telescope, but with a piece of chalk and a blackboard. It emerged from the most beautiful and revolutionary set of equations ever written, Albert Einstein's theory of general relativity. Published in 1915, these equations described gravity not as a force, but as a curvature of spacetime itself, warped by mass and energy. Almost immediately, physicists began playing with these equations, searching for their hidden secrets. Just a year later, Carl Schwarzschild found a solution that described the gravity around a perfectly spherical, non-rotating mass. His math revealed a point where the curvature became so extreme that it created a boundary from which nothing could return, an event horizon. But this was viewed as a mathematical oddity, a theoretical ghost in the machine. Surely, nature would never actually produce such an absurd thing. For decades, these dark stars remained a curious footnote, a fascinating but implausible implication of the new physics. Even Einstein himself doubted they could be real. The true turning point came in 1963, when a young New Zealand mathematician named Roy Kerr tackled a far more complex problem. He asked a simple but profound question: what if the black hole was spinning? Almost everything in the universe rotates, from planets to galaxies. A stationary black hole seemed like an unrealistic simplification. Kerr's solution was a stroke of genius, an elegant set of equations that described the spacetime around a rotating mass. His work unveiled the entire bizarre architecture we've been exploring: the Ergosphere, where space itself is dragged, the ring singularity, and the oblate event horizon. The Kerr metric didn't just make black holes more realistic, it made them infinitely more interesting. It provided the precise mathematical blueprint for the very journey we've been narrating. Yet, mathematics alone isn't enough to prove something exists. For years, black holes remained a theorist's paradise but an observer's nightmare. How do you see something that emits no light? The first major clues came from the discovery of quasars in the 1960s. These incredibly bright, distant objects shone with the power of 1,000 galaxies from a region not much larger than our solar system. The only conceivable engine powerful enough to fuel such a beacon was the gravitational energy of a supermassive black hole, sucking in vast quantities of gas and converting its mass into blinding radiation. Then came the discovery of X-ray binaries within our own galaxy, like Cygnus X1. Astronomers observed a visible star orbiting an unseen, massive companion, with intense X-rays screaming out from the region where the companion's gravity was tearing the star apart. The math was undeniable. The invisible object was too small and too massive to be anything other than a black hole. Piece by piece, the evidence mounted, transforming these mathematical monsters into accepted celestial citizens. The final, breathtaking confirmation arrived astonishingly recently. In 2019, the Event Horizon Telescope collaboration released the first ever direct image of a black hole's shadow. This wasn't an image of the black hole itself, but of its silhouette, the dark circle where light disappears, surrounded by a fiery ring of lensed photons from the accretion disk. The target was the supermassive black hole at the heart of the galaxy M87, a behemoth weighing in at 6.5 billion times the mass of our Sun. The image was a perfect match for the predictions of general relativity and the Kerr solution. It was a monumental human achievement, requiring a virtual telescope the size of Earth itself and years of painstaking data analysis. It moved black holes from the realm of inferred existence into the realm of visceral, tangible reality. This entire history, from a controversial mathematical solution to a direct photograph in just over a century, is a stunning testament to human curiosity and ingenuity. It shows us that our understanding of the cosmos is constantly evolving, and that the most outlandish ideas can become established fact with patience and proof. This context makes our thought experiment so much more powerful. We aren't just fantasizing, we're extrapolating from a solid foundation of science that was built, one brilliant insight at a time, by people who dared to take the math seriously. This journey into the abyss, for all its bizarre physics and cosmic spectacle, is at its core a story about endings. It holds up a dark mirror to our most profound human anxieties, the fear of death, the mystery of what comes after, and the haunting question of whether our existence holds any lasting meaning. Falling into a black hole is the ultimate metaphor for oblivion, but writ on a cosmic scale. It takes the personal, private dread of our own mortality and projects it onto the grandest possible screen, allowing us to explore these deepest of questions from a safe distance through the powerful lens of scientific imagination. Confronting this inevitable dissolution forces a radical shift in perspective. On Earth, our lives are filled with constructs of our own making, ambitions, rivalries, the daily grind, that feel overwhelmingly significant. But against the backdrop of a supermassive black hole, these concerns shrink into utter insignificance. You are not a CEO, an artist, or a parent in that moment. You are a collection of atoms, a temporary pattern in the cosmos about to be unraveled and recycled. This isn't a nihilistic realization, but a strangely liberating one. It invites a profound humility, a recognition that we are an infinitesimally small part of a universe whose workings are far grander and more mysterious than our everyday lives can ever capture. Your individual story may end, but you are reabsorbed into the ongoing billion-year story of the universe itself. your energy becoming part of the black hole's future, and through Hawking radiation, perhaps eventually re-entering the cosmic cycle. The experience also touches on the ancient philosophical puzzle of consciousness. Is the mind simply the product of a physical brain, and if so, what happens when that physical structure is torn apart? If your consciousness is accelerated in those final seconds, granting you a hyper-realistic review of your entire life, does that represent a final, glorious firing of neurons or something more? While there's no scientific evidence for a soul or an afterlife, the sheer strangeness of the scenario pushes us to the very limits of what we can comprehend about the self. The black hole doesn't just destroy the body, it challenges our very definition of where we end and the universe begins. Ultimately, this thought experiment is less about the grim reality of being spaghettified and more about what that hypothetical end can teach us about life right now. It encourages a kind of cosmic perspective, a reminder that our time is precious and finite, and that the universe is a place of breathtaking wonder and terror. To contemplate such an end is to be jolted into a greater appreciation for the fragile, beautiful improbability of our existence here on a pale blue dot. It's a call to look up at the night sky not with fear, but with a deep and humble curiosity, embracing the mysteries that remain and valuing the brief, brilliant moment of consciousness we are given. This philosophical resonance is what transforms a cold physics problem into a deeply human story, one that has captivated scientists and poets alike for decades. While our journey has been guided by the cutting edge of theoretical physics, for most people, their first and most vivid encounter with a black hole comes not from a scientific journal, but from the silver screen. Hollywood has long had a love affair with these cosmic mysteries, using them as backdrops for epic adventures and mind-bending narratives. Perhaps the most famous and scientifically ambitious portrayal is Christopher Nolan's 2014 film Interstellar. The film's depiction of the black hole gargantua is nothing short of iconic, a massive, swirling, luminous disk with a shimmering accretion ring, warping the starlight around it into a perfect halo. It's a breathtaking image that brought the awe and majesty of these objects to life for millions of viewers. The filmmakers even collaborated with Nobel Prize-winning physicist Kip Thorne to ensure the visual effects for gravitational lensing were based on real equations, resulting in a portrayal that was, in many ways, the most scientifically accurate ever seen in popular media. However, this commitment to visual realism was carefully balanced with the need to tell a compelling story, and that's where artistic license takes over. The most dramatic liberty is the film's central plot device, the ability of the characters to travel through the black hole's singularity and interact with a higher dimensional realm that allows them to manipulate time and communicate with the past. While the concept of a five-dimensional tesseract is a fascinating speculative idea, it moves firmly from established science into the realm of science fiction. In reality, as we've explored, the tidal forces and quantum effects near a singularity would almost certainly destroy any complex information or structure long before such an experience could occur. The film also streamlines the experience of time dilation for narrative punch. While the crew on the water planet ages years in just hours, their personal experience of that time is shown as normal. In a real scenario, from their own perspective, those years would have felt like years, a subtle but important distinction that highlights how film often compresses complex relativistic effects for dramatic clarity rather than absolute accuracy. This isn't a criticism of Interstellar or other films. It's simply an acknowledgement of their different goals. Movies like Event Horizon or the recent The Black Hole animation use these objects as settings for horror and adventure, prioritizing mood and metaphor over scientific fidelity. They are in the business of wonder and storytelling, not education. The potential downside is that these powerful, simplified images can cement misunderstandings in the public consciousness. Viewers might come away believing that black holes are literal tunnels to other dimensions, that you could survive a trip through one, or that they behave like unpredictable vacuum cleaners roaming through space, sucking up everything in their path. These misconceptions, while harmless for entertainment, can create a barrier to appreciating the true, and in many ways even more fascinating, reality of black hole physics. The real value of these cultural touchstones is their incredible power as a gateway. A visually stunning scene in Interstellar or a thrilling plot in a sci-fi novel can spark a curiosity that leads someone to search for deeper answers. They engage our emotions and our imagination in a way that a dry textbook simply cannot. This initial engagement is priceless. It gets people asking questions, and that's where scientists and educators can step in to separate the cinematic fantasy from the physical fact. By understanding the liberties taken by filmmakers, we don't diminish our enjoyment of their art, we enhance it. We become more critical and appreciative viewers, able to marvel at the artistic achievement while also understanding the real science that inspired it. This balanced perspective allows us to enjoy the thrilling fiction while remaining grounded in the astonishing truth, a truth that is currently being uncovered by teams of researchers using tools far more powerful than a camera lens. Even with the incredible progress we've made, from mathematical prediction to direct imaging, the true nature of a black hole's interior remains the final frontier of our understanding. Everything we've described about the fall through a rotating black hole is based on the rock-solid foundation of Einstein's general relativity, but physicists know that this is only part of the story. Once you cross that event horizon, you enter a realm where the immense gravitational forces operate at such tiny scales that the quantum nature of the universe must take over. And right now, we simply don't have a complete theory that successfully merges the cosmos' governing rules of gravity with the subatomic, probabilistic world of quantum mechanics. This grand challenge, the quest for a theory of quantum gravity, is the single biggest unsolved problem in fundamental physics, and the violent heart of a black hole is the perfect laboratory to test our ideas. Scientists aren't just theorizing from armchairs, they are using some of the most advanced tools ever conceived to probe these mysteries. Supercomputers around the world are running incredibly complex simulations, crunching the numbers of general relativity to model the collisions of black holes and the behavior of the turbulent plasma in their accretion disks. These simulations give us a glimpse into dynamics that are otherwise invisible, helping us interpret the signals we detect and what signals they are. The dawn of gravitational wave astronomy with LIGO and Virgo has opened an entirely new window onto the cosmos. We are no longer just seeing the universe, we are now listening to it. The chirps and rumbles picked up by these exquisite instruments are the direct soundtrack of spacetime itself, ringing like a bell from the cataclysmic mergers of black holes billions of light years away. Each detection is a treasure trove of data, allowing us to measure the spins, masses, and properties of these dark objects with stunning precision, and providing crucial tests for whether they behave exactly as Kerr predicted. Yet for all this power, the deepest questions persist, and they are profoundly puzzling. One of the most heated debates centers on the idea of a firewall. The classical view we've presented suggests you would cross the event horizon smoothly, feeling nothing special at that moment. But when physicists apply quantum field theory to this region, some calculations suggest that instead of empty space, the horizon might be a seething wall of ultra-high-energy particles, a literal firewall that would incinerate any infalling object instantly. This isn't just a minor discrepancy. It represents a direct contradiction between two pillars of modern physics, and resolving this paradox is crucial to understanding what truly happens at the point of no return. Then there's the enduring enigma of the information paradox, which we touched on earlier. The conflict between quantum mechanics' demand that information be preserved and general relativity's suggestion that it is lost down a black hole remains unresolved. New ideas are constantly emerging, like the concept of soft hair, which suggests that information might be encoded on the event horizon itself in subtle, low-energy quantum states. Others propose that black holes might not have interiors at all in the way we think, or that our concept of a strict, localized event horizon might need to be replaced with a fuzzy, quantum-bathed boundary. Rotating black holes with their more complex geometry are the perfect testing ground for these wild ideas. Their Ergosphere and Ring Singularity provide a richer mathematical landscape for theories like string theory and loop quantum gravity to make testable predictions about how they might alter the fate of an infalla or how information could potentially escape. This entire endeavor is a powerful reminder that science is a living, breathing process of inquiry, not just a collection of settled facts. The description we've woven together in this video is the best story we can tell based on our current knowledge, but it is a story that is still being written. The next generation of telescopes, both on the ground and in space, along with more sensitive gravitational wave detectors, will undoubtedly bring new data that will force us to revise, adapt, and sometimes completely overhaul our models. This uncertainty isn't a weakness, it's the very engine of discovery. It's what drives scientists to ask the big questions and push the limits of human comprehension, embracing the unknown with a mixture of humility and relentless curiosity. Yet this entire incredible journey we've been narrating is, and will hopefully always remain, a purely mental exercise. No human is ever likely to take this plunge, and no spacecraft could possibly survive it. So, a fair question arises: what is the real value of spending so much time and intellectual energy on a detailed fantasy of our own destruction? The answer lies in the profound power of the thought experiment itself, a tool that has been sharpening human understanding since long before we had laboratories or telescopes. By rigorously following a hypothetical scenario to its logical extreme, we are forced to confront the limits and implications of our own theories. Imagining the fall into a rotating black hole isn't just a fun diversion. It is a brutal stress test for the laws of physics as we know them. It pushes general relativity to its breaking point, revealing where its predictions become paradoxical or break down entirely. And in doing so, it illuminates the path toward a deeper, more complete theory of the universe. This process of imaginative exploration is what led Einstein to his breakthroughs, and it continues to drive theoretical physics forward today. The practical benefits of this kind of thinking are far more tangible than you might expect. The need to understand the subtle effects of gravity and time dilation on orbiting satellites, for instance, directly led to the crucial relativity corrections baked into the global positioning system. Without accounting for these effects, which tell us that clocks on GPS satellites tick slightly faster than those on Earth, the entire system would become useless, accumulating errors of several kilometers per day. The same fundamental physics that describes the extreme time warping around a black hole is essential for making your phone's map application work. Furthermore, the immense computational challenges of simulating black hole mergers and accretion disks have driven innovations in supercomputing and data analysis techniques that ripple out into weather forecasting, medical imaging, and financial modeling. The pursuit of knowledge about the most extreme objects in the cosmos consistently spins off technologies that improve our daily lives right here on Earth. However, with this great power of imagination comes an equally great responsibility for clarity. For every meticulously researched portrayal of a black hole like the one in Interstellar, there are a dozen more that play fast and loose with the science, presenting wormholes as magical portals or singularities as gateways to other dimensions without the crucial context of this is speculative. This blurring of the line between established science and science fiction, while entertaining, can sow confusion and lead to widespread misconceptions. It's vital to maintain a clear distinction between what we know based on evidence and mathematical consistency, and what we are imagining as a compelling possibility. The true beauty of a thought experiment lies in its intellectual honesty. It follows the known rules to see where they lead, and it is upfront about the point where those rules become unknown. This careful balance between creative imagination and rigorous adherence to evidence is the very heart of good scientific communication. It builds public trust and fosters a genuine, nuanced appreciation for how science actually works, with all its thrilling certainties and its honest uncertainties. Ultimately, these journeys into the impossible are a celebration of human curiosity itself. They are a testament to our unique drive to ask, what if? And to follow that question wherever it may lead, regardless of any practical application. A child wondering what it would be like to fall into a black hole is engaging in the same fundamental process as a physicist running a supercomputer simulation. Both are exploring the consequences of physical laws through the power of their own minds. This innate curiosity is our greatest engine of discovery. It fuels not only scientific progress but also educational passion, inspiring new generations to look up at the night sky with wonder and to pursue the math and physics needed to truly understand what they are seeing. By giving ourselves permission to explore these extreme and fatal scenarios in vivid detail, we are not indulging in morbidity. We are honoring our deepest desire to comprehend the universe in its entirety, from the gentle fall of an apple to the violent, spinning heart of darkness itself. Trying to wrap your mind around the mind-bending physics of a black hole can feel like an impossible task, which is why we often turn to the familiar to make sense of the utterly alien. Think of the black hole's spin, that incredible frame-dragging effect, not as some abstract force, but as a powerful river current. If you were to try and swim directly against the flow of a raging river, you'd be swept downstream no matter how hard you fought. Now imagine that the river itself is made of the very fabric of spacetime. That's the Ergosphere. Even if you were in the most powerful rocket ship, firing all thrusters to stay in one place, the current of spinning space would still carry you along. You wouldn't be fighting against water, but against the foundational grid of the universe itself, and it is a fight you cannot win. This analogy gives you a visceral sense of that unstoppable cosmic drag. For the gruesome process of spaghettification, a common comparison is to imagine yourself as a lump of dough being pulled and stretched by a relentless force. At first, the pull is gentle, a slight tension you can barely feel, but that force keeps increasing, stretching you longer and thinner, while simultaneously squeezing your sides inward. The metaphor works because we can all picture that string of pizza dough being twirled and elongated. But to make it accurate to a black hole, you'd have to imagine that every single atom in that dough is also being pulled. The atoms in your fingertips feeling a stronger tug than the atoms in your elbow, stretching the very molecular bonds that hold you together until they scream and finally snap. It turns a simple kitchen image into a horrifyingly personal illustration of tidal forces. We use these mental shortcuts because our brains are not built to intuitively grasp infinite density or warped spacetime. They are evolutionary tools designed for life on Earth, for navigating a world of medium-sized objects moving at slow speeds. Analogies act as a conceptual bridge, allowing us to walk partway across the chasm between what we know and what physicists calculate. They translate the cold, hard math of the Kerr metric into a language of sensation and experience that we can actually feel in our bones. This translation is not a dumbing down of the science. It is a vital tool for building a foundational understanding, a first step toward appreciating the deeper, more complex mathematics. However, every analogy has its breaking point, and it's crucial to recognize where these comparisons fall short. That river current of frame dragging is a powerful image, but a river has a surface and a bank. You can see its edges. The current in a black hole's ergosphere is invisible and permeates everything. It is space itself. There is no bank to swim toward for safety. Similarly, the dough analogy for spaghettification fails to capture the sheer, violent chaos near a rotating singularity, where the forces aren't uniform and smooth but might twist and shear you in multiple directions at once. No earthly experience can truly prepare you for the reality of having your left side experience time at a different rate than your right side. These metaphors are a starting point, a way to get your foot in the door of understanding, but they are not the entire mansion. They give us a glimpse, but the full, terrifying majesty of a black hole remains, for now, beyond the limits of our everyday imagination. But what if you could embark on this terrifying voyage without paying the ultimate price? What if you could stand at the precipice of a black hole and peer into the abyss, all from the safety of your own home? This is no longer a fantasy. Using the very equations we've been discussing, the complex mathematics of the Kerr metric and general relativity, scientists and programmers are now constructing incredibly detailed virtual reality simulations that allow anyone to experience a fall into a black hole. These are not video games with science fiction magic. They are rigorous digital recreations, painstakingly built to follow the actual laws of physics as we understand them. By feeding Einstein's rules into powerful game engines, researchers can calculate how every single photon of light would bend around the warped spacetime, creating a visual and sensory experience that is, for all intents and purposes, the closest any human will ever get to the real thing. The primary power of these simulations lies in their ability to transform abstract theory into tangible, visceral experience. You can put on a VR headset and find yourself in the cockpit of a spacecraft, watching as the stars around you begin to smear into arcs of light. You can feel a genuine sense of awe as the accretion disk wraps around the black hole's shadow, forming that brilliant, complex halo of fire. You can even turn your head and see the phantom images of your own ship from moments ago, a disorienting effect that no textbook description could ever hope to convey with the same impact. This is experiential learning at its most profound. It allows students and the public to not just learn about frame dragging, but to actually feel a semblance of its unstoppable pull, to not just read about spaghettification, but to witness the universe itself distorting around them. These tools have become invaluable for public outreach at planetariums and science museums, captivating audiences and making the incredibly complex physics of black holes accessible, engaging, and unforgettable. Of course, these digital journeys are not perfect replicas. They are, by necessity, simplified models. The simulations typically cannot yet account for the chaotic quantum effects that might dominate the final moments near the singularity, and the sheer computational power required to render every single particle in a turbulent accretion disk in real time is still beyond our reach. The experience is also sanitized, free from the lethal radiation and the visceral, body horror of tidal forces. Yet these limitations don't diminish their achievement, they highlight it. By creating a compelling approximation, these virtual experiences accomplish something perhaps even more important than perfect accuracy. They ignite curiosity. They provide a powerful gateway that inspires users to ask deeper questions, to seek out the underlying science, and to understand why the simulation behaves in such bizarre and counterintuitive ways. It turns passive observers into active participants in the greatest story the universe has to tell. This technological innovation represents a monumental shift in how we explore the cosmos. For centuries, our only tools were telescopes, which allowed us to observe from a distance. Then came space probes, which allowed us to visit other worlds. Now, with virtual reality, we have entered a new era, the age of digital immersion. We can now travel to places that are fundamentally unreachable by any physical spacecraft, to environments so hostile they would vaporize any probe instantly. We can explore the interior of a black hole not with a robotic mission, but with our own senses, guided by the unerring logic of mathematics. This brings these cosmic wonders to life for millions, democratizing access to the frontiers of theoretical physics and allowing everyone to share in the awe and wonder of discovery. It is a testament to human ingenuity, our ability to use our minds to build a window into the most extreme environments nature can devise, and in doing so, to better understand our place in a vast and often terrifying universe. This relentless curiosity about black holes is far more than a niche scientific interest. It is a fundamental expression of who we are as a species. Since the first humans looked up at the night sky and wondered about the points of light overhead, we have been driven to explore the unknown, to push beyond the boundaries of the familiar. Black holes represent the absolute pinnacle of that journey, the most extreme, mysterious, and awe-inspiring phenomena we have yet discovered. They are the ultimate frontier, not of geography, but of knowledge itself. They challenge our most brilliant minds, forcing us to stretch the very limits of our intellect and creativity to even begin to comprehend their nature. This isn't just academic exercise, it is a profound engagement with the deepest laws that govern existence, a puzzle that taps into a universal human desire to make sense of the cosmos and find our place within its vast, often incomprehensible scale. This deep-seated fascination is a powerful engine for progress. The drive to understand something as bizarre as a space-time singularity has led to tangibly advancements that ripple through our technology and society. The need to test the predictions of general relativity around black holes, for instance, pushed us to develop incredibly precise atomic clocks and systems for the global positioning system, because without accounting for these subtle relativistic effects, your phone's map would be useless within minutes. The algorithms developed to clean up the data and construct the first image of a black hole's shadow by the Event Horizon Telescope collaboration are now being used to improve medical imaging techniques, potentially leading to earlier disease detection. The pursuit of pure, fundamental knowledge, driven by wonder and curiosity, consistently spins off innovations that benefit our daily lives in unexpected ways, proving that the line between abstract theoretical physics and practical human application is often surprisingly short. Beyond the technological spin-offs, this quest fulfills a deeper, almost philosophical need. In a world often consumed by immediate concerns and divisive conflicts, black holes offer a humbling and unifying perspective. They remind us that we are all, regardless of our earthly differences, inhabitants of a small planet orbiting an average star, looking out at a universe filled with wonders beyond our imagination. Contemplating an object that can warp time and swallow light puts our daily struggles into a cosmic context, not to diminish them, but to inspire a sense of shared awe and collective purpose. It speaks to a yearning for meaning that transcends individual lives, connecting us to a grand, billion-year narrative of cosmic evolution. This ability to inspire wonder and remind us of our shared humanity is, in its own way, just as valuable as any technological breakthrough, fueling our collective imagination and ambition for a better future. While our journey has been a hypothetical one, the tools that will transform these thought experiments into tangible data are already taking shape on the drawing boards and in the clean rooms of the world's leading space agencies. The next generation of astronomical observatories promises to do more than just give us a better picture. They will allow us to listen to the universe in an entirely new way and peer into the heart of darkness with unprecedented clarity. Leading this charge is a mission that seems ripped from the pages of science fiction: the Laser Interferometer Space Antenna, or LISA. Unlike its ground-based predecessors like LIGO, which made the first historic detections of gravitational waves, LISA will consist of 3 spacecraft flying in a perfect triangular formation, trailing behind Earth in its orbit around the Sun. These satellites will be connected by laser beams over a staggering distance of 2.5 million kilometers, creating the most sensitive measuring device ever built. This colossal instrument is designed to detect the low-frequency gravitational wave hum that fills the cosmos, a frequency range where the universe's most massive objects do their dance. This is where supermassive black holes sing. When 2 of these behemoths, each millions of times the mass of our Sun, spiral toward a cataclysmic merger, they warp spacetime itself, sending out ripples that travel across billions of light years. LISA will be able to hear this song with incredible precision, but for rotating black holes, the data will be even richer. The specific waveform, the unique pattern of the gravitational wave signal, carries an imprint of the black hole's spins. By analyzing the subtle twists and tremors in this signal, scientists will be able to determine not just the mass of the merging black holes, but also the exact speed and orientation of their rotation. It will be like a cosmologist's fingerprint, allowing us to test the predictions of the Kerr metric with a precision we can only dream of today, potentially confirming if reality truly matches the elegant mathematics we've been relying on. But the ambition doesn't stop at observing black holes from the outside. Future missions are being conceived with the explicit goal of probing the immediate environment of the event horizon itself. The next iteration of the Event Horizon Telescope project aims to add space-based telescopes to its existing global array of radio dishes. By placing observatories in orbit, we could create a virtual telescope with a baseline as wide as the distance from the Earth to the Moon, achieving exponentially sharper resolution. This could allow us to create not just a static image of a black hole's shadow, but a high-definition movie showing the turbulent flow of plasma in the accretion disk in real time. We might directly observe the frame-dragging effect as matter is whipped around the ergosphere, watching the predicted whirlpool of spacetime in action. This would move us from inference to direct observation, providing visual evidence for the bizarre environment we've been describing. The ultimate goal, however, remains the most challenging: to find a way to test what happens inside the event horizon. Since no information can escape, this seems like an impossible task. Yet, physicists are nothing if not creative. Some theories suggest that the key might lie in the subtle quantum properties of the Hawking radiation emitted by a black hole. Advanced instruments, perhaps placed far in the future, might be able to analyze this radiation for any faint, encoded traces of what fell in, offering an indirect window into the black hole's interior. Other speculative ideas involve using the gravitational waves from a merger to probe the nature of the singularity itself, the final ring-down phase of a merger, the moment when the new, larger black hole settles into a stable shape might contain echoes or other subtle signals if the interior structure differs from our classical predictions. Finding such an echo would be revolutionary, the first direct evidence that our understanding of the singularity is incomplete and that new physics, likely involving quantum gravity, is at play. These forthcoming advancements ensure that the story of black holes is far from a closed book. Every new mission, every more sensitive detector, has the potential to deliver a data point that completely upends our current models. The description we've woven together in this video is our best current understanding, a snapshot of a theory in flux. It is a compelling narrative built on a century of brilliant theoretical work and a recent explosion of observational evidence. But it is not the final word. The true excitement lies in this constant state of becoming, in knowing that the cosmos is always ready to surprise us. Staying engaged with these developments means watching the scientific method unfold in real time, a process of rigorous questioning, prediction, and discovery that continues to push the boundaries of human knowledge and redefine our place in this vast and astonishing universe. So let's take a moment to gather our thoughts after that incredible voyage, to piece together the entire journey from the first glimmer of the accretion disk to the final, theoretical whispers at the Ring Singularity. We began with the approach, watching the cosmos itself warp around us as the black hole's gravity bent starlight into a perfect, shimmering halo. We felt the initial, unsettling tug of tidal forces, that slow and inexorable pull that would eventually lead to spaghettification, a process made slightly more gradual and bizarre by the black hole's spin, stretching our very atoms into a cosmic stream. We crossed the event horizon not with a bang, but in utter silence, a smooth passage into a realm where the laws of physics as we know them cease to apply, where time and space swap their fundamental roles. Inside, we were swept into the Ergosphere, caught in the irresistible current of frame-dragged spacetime, a cosmic whirlpool from which there was no escape. Our perception of time shattered completely. While our own clock seemed to tick normally, the entire external universe accelerated into a blinding montage of its own future, all while any distant observer would see our final moment frozen for eternity. Our senses were overwhelmed by phantom images and impossible light shows, with the accretion disk wrapping around us in a complex lattice of fire, and the ghostly afterimages of our own descent flickering in the distorted void. This visual carnival was matched by a psychological odyssey, a journey from sheer primal terror through to a state of awe and profound humility, and finally to a quiet acceptance as we became part of something infinitely larger than ourselves. We grappled with the most speculative ideas of all, the possibility that the Ring Singularity might not be an end, but a gateway to other universes or distant parts of our own, a tantalizing what if that remains one of physics' greatest unanswered questions. And we confronted the chilling yet fascinating paradox of information, the notion that some quantum echo of our existence might be encoded in the Hawking radiation that will slowly, over eons, leak back into the universe. This entire narrative has been a blend of the stark, unforgiving physics of general relativity and the deeply human experience of confronting the ultimate unknown. It's a story that ties the cold equations of the Kerr metric to the very real sensations of wonder, fear, and curiosity, creating a comprehensive picture of what it might mean to fall into one of the universe's most magnificent and terrifying creations. This recap isn't just a summary, it's an integration of every bizarre and profound moment, weaving them into a single, unforgettable tapestry of a journey to the edge of reality. Falling into a rotating black hole is so much more than a one-way trip to oblivion. It is the ultimate journey through the extremes of physics and human perception, a profound exploration that blends sheer terror with indescribable beauty and deep, enduring mystery. While the outcome is undeniably fatal, the hypothetical voyage offers us something priceless, a window into the fundamental nature of reality itself, challenging everything we think we know about time, space, and our own existence. It pushes the boundaries of our imagination and forces us to think far beyond the comforting confines of our everyday experience, reminding us that the universe operates by rules that are far stranger and more wonderful than we can often conceive. This entire adventure, from the first visual distortions of the accretion disk to the mind-bending chaos near the Ring Singularity, serves as a powerful testament to human curiosity. It underscores our relentless drive to ask big questions, even about scenarios we can never physically experience, and to seek answers through the potent blend of scientific rigor and creative thought. As the visionary astronomer Carl Sagan once reflected, "Somewhere, something incredible is waiting to be known." That sentiment captures the very heart of why we embark on these mental expeditions into the unknown. We may never send a probe into a black hole, let alone a person, but by daring to imagine it, by applying our best mathematics and physics to the problem, we come to know the universe a little better. We inch closer to understanding the profound mysteries that lie at the intersection of gravity, quantum mechanics, and time. This exploration does more than just satisfy scientific curiosity. It invites a deep sense of humility and awe. Confronting the immense power and scale of a black hole highlights our own tiny place in the cosmos, not to diminish our significance but to expand our perspective. It encourages us to look up at the night sky with a renewed sense of wonder, to appreciate the incredible fact that we are conscious beings capable of contemplating such magnificence. The journey reminds us that the universe is filled with wonders beyond our current comprehension, and that the spirit of exploration, whether virtual or physical, is one of humanity's most noble and defining traits. Thank you for joining me on this incredible hypothetical adventure through one of the most extreme environments in the cosmos. If this journey sparked your curiosity, I invite you to share your own thoughts and questions in the comments below. What part of the descent fascinated or surprised you the most? For more deep dives into the mysteries of space, from the birth of stars to the search for alien life, be sure to subscribe and hit the notification bell so you never miss an exploration. Until our next voyage into the unknown, keep looking up and wondering about the incredible universe.